a cohomology here. MU is a spectrum called the tone spectrum, and I thought I'd start off first at the end of where we're gonna go in this big journey with the importance of MU. It has this property called the Nilpotence theorem, and it is very good at detecting nilpotent elements in stable homotopy groups. For any ring spectrum E, if you take a look at the kernel of this thing called the Boardman homomorphism, which is induced just by the unit map of S0 into E, the kernel of this thing is exactly all of the nilpotent elements in the stable homotopy group. This is one of the versions of it. I think there's like 2 other versions, but this is the version that I wanted to put up there just because it really highlights how important MU is in this whole story. So with that out of the way, I'm going to define MU theory.
The quick question is ring spectrum just something which has a E smash E to E map or like?
Yes, unit map from the sphere spectrum, E smash E. I don't know if we need any structure like A infinity or E infinity. I didn't see that.
Okay,
Yeah, this is all the structure that I remember seeing in Ravenel, like 1.5 something. So yeah, to start off, we're going to do some geometry. So to start off, there's a few things I'm just going to take that you know. You already know what a complex vector bundle is. You should know that if I have 2 bundles, psi 1, psi 2, I can form their direct product, or I can form their tensor product, either way. You should know about Grassmannians. I'm going to call them this. The Grassmannians of K-planes and n-space over some field F. And we have universal bundles over the spaces of this form. You can bundle all of these together, unintended, and get classifying spaces called BUN for the complex case, or BON for the real case. We're not really going to use real vector bundles that much, but Ravenel talks about them. So with these out of the way, the first thing we're going to talk about spaces and spectra. So for any vector bundle that we have, call this B. If B is what's called paracompact, there always exists a thing called a Hermitian metric, which I like to write as this. Looks very much like a dot product from standard vector spaces. On the total space, so over each fiber on that complex vector space, it looks like a Hermitian metric. You can use this to get a length on your vector bundle. That'll allow us to construct other bundles. We're going to have a lot of bundles in this first section of the talk. First thing we're going to talk about, those regards, our disk and sphere bundles. Attaching the vector bundle.
Do you know why Ravenel uses Hermitian metrics as opposed to like Riemannian? Does it make a difference?
I believe it does, since these are complex vector bundles. Hermitian vector bundle or Hermitian metrics are those metrics on the bundles that act nicely. So if you take 2 vectors, you're guaranteed, like for any general vector V and W, that'll map you down into C. But if you take the self length, that'll get you into R. That'll get you an actual good length. So I believe that's why he's using Hermitian metrics.
Right, I'm just saying for the purpose of building the top space, like you can put a Riemannian metric and it'll give you the same thing. That's why I was wondering.
I don't believe it comes up in any specificity. I think that's just the language he uses. But these things, the important part that they do is this length here allows us to form distant sphere bundles, which unsurprisingly, I'm going to denote D of P and S of P. D of P, I'm going to talk about what they act as over the fibers of B. I don't want to give the actual concrete description. So over any given fiber on this thing, it's going to be the set of vectors V that said its length is less than or equal to 1. Sphere bundle, similar. Set of vectors such that the length is 1. Naturally, you can see that this thing has an inclusion in that dude, and that gives us the first term we'll see in this talk. The Tom space of that bundle. With this inclusion, we're going to do the one natural thing we can do. We're going to mod it out. This quotient by the sphere. This will give us the Tom space of the vector bundle. There's a very lovely theorem that's covered at the end of like 526 called the Tom isomorphism theorem. You can use it to explicitly do some homology calculations. It's in the sections of Ravenel. I'm just going to put them up on the board without much proof. So we're not going to go over Tom isomorphism, Tom classical, all that stuff. There are my notes. This out of the way. Then we're going to define what MU is at a specific degree M. I just erased what I wrote as a universal bundle, which is kind of unfortunate. But if we have a universal bundle of n planes over the Grassmannian, no, check myself in the leg. We're going to also call the bundle given n. I'm using notation very heavily. The nth Tom space is then the Tom space attached to this bundle. So it is heavily related to classifying certain bundles. There's also a description of this as a homology theory related to cobordism. Since that's not very important to what we're going to talk about in the seminar, I decided to not do that. But generally we have that. You can also form a spectrum out of this. The 2n space of it is mu of n. The 2n plus first space of it is the only thing it can be if you want to do a spectrum, the suspension of mu. So as of now with this construction, are there any questions before we go into more stuff?
One question. So what happens if we take like loops of MUN plus 1 or MUN plus 1 or something? Does that work or?
I believe, let's see.
Or is it the same thing?
It should be the same thing. I don't know, however, not too familiar with spectra, and also it isn't in Ravenel. But since it's a very nicely structured spectrum, I'd assume taking the loops would be adjoint in some manner. Somebody knows, please tell me.
If you know you want to go homology theory anyway, so you want an omega spectrum, then that should be fine because that's required to be true anyway.
Yeah.
So like maybe once you like, if this isn't an omega spectrum, then once you replace it, you're gonna get that.
Yeah,
Okay,
exactly.
But I was just wondering if it is like on the nose direct.
Yeah, I don't know.
Yeah, Ravenel makes no mention of needing to construct around it, so I'm just gonna assume it is. I feel like he would say.
Well, on the
Like,
nose,
okay,
it definitely isn't, but up to equivalence, it definitely is.
I meant up to equal.
Oh, okay.
There you go. Thank you. Okay, so you got this. You notice we haven't given a map from the suspension of this to mu of 2n plus 2. That's what I'd like to do here. It relies on this thing called planification of a map. Which is fairly simple. If I have two vector bundles, b prime, b, sum 0, f1, p, and p prime. This will end up giving a map of tone spaces. So you get T, just the total thing F, T of P prime, T of P This is how we're going to construct the product on MU. This is how we're going to do the suspension over there. It is a lot of structure related to MU. From this tomification, one thing that you immediately get, if you take the tone space of a direct sum of bundles, convert it to its match product. We sum it with a trivial line bundle, I believe. Yeah, trivial complex line bundle. This ends up smashing it with S2. Again, same as double suspension. Of that vector bundle. Okay. Now to go about constructing the suspension over there that will fully make it into a suspension spectrum. It's a very lovely inclusion. That takes the classifying space for n-dimensional vector bundles and includes it in here. This on the level of vector bundles is exactly taking the vector bundle and direct summing it with a complex line bundle. Do you have a question?
No, sorry.
That's all good. And so with this right here, this will allow us to basically take the suspension of mu 2n plus 1, which is a double suspension, mu 2n. From what we saw here, this is one of the words he uses, like classifies, classified by. I'll map them on the right line for a second. What we have there, this is true. We can apply the tomification of that map J and end up at T of gamma n plus 1, which is exactly where we wanted to end up at. 2 times n plus 1. So that gives us the suspension map from the suspension of mu 2n plus 1 to mu of 2 times n plus 1. And now we have a lovely spectrum that we can start doing cohomology and topology. And before we go too heavy in the algebra, there's one other sort of motivating property of the tone spectrum. It is what's called a universe. It is the universal complex-oriented cohomology theory. We get like one proof in this section. It's nice to have. And once we start talking about the Landweber exact functor theorem in like 2 lectures, this is going to give another bridge. MU to spectra. So, a cohomology theory, I'm going to call E star, is complex oriented if there is some class, I call it, or it's complex orientable. If the inclusion, the method induced by inclusion, taking CP infinity into that is a surjection. Since this is a cohomology theory, this is isomorphic to just the cohomology or the homotopy ring of E. And so we say a given element is a complex orientation if in this composite map that element goes to 1. And this is a complex orientation of that cohomology theory. If you look, oh, I erased all of it. From the definition, it's not too hard to show that mu0 is the sphere spectrum. If you want to look at sphere bundles over a point, that is just a sphere. You take the the spectra as you go up, and that becomes the sphere spectra.
A quick nitpick, that should, the pi star would be, that should be pi 0 be, right?
Yeah,
Yes, I believe you're right. I have that in there. I'll make a change. I'm gonna post lecture notes. I had that as pi star for some reason. Thank you for pointing that out.
so when you say the inclusion S2 to CP infinity,
Yes, believe that is S2 into C1 into CP. Okay. So just
Yeah.
all more inclusions as you go along.
is that the same thing as the canonical line bundle on S2? Because CP infinity classifies
Mhm.
line bundles.
I think it is, that comes up in like 3 seconds.
It is, and that include, that first inclusion is actually a homework.
Yes. Following that, you go up one level. I didn't see a nice proof of this, but one thing you can think about for these tone spectra, actually this is just a tone space. Generally, for positive n, this ends up being the quotient space of un by un minus 1. So you can see that for 1, this is just CP infinity. And so, if you basically follow this around, this inclusion here acts like the unit map for this as a spectrum, giving the existence of a complex orientation, which I have called X and U. So now MU is a complex oriented cohomology theory. It is the universal one. So you have any other complex oriented cohomology theory B star, that the complex orientations are in bijective correspondence with homotopy classes of maps from MU into that A star. I got the direction right, I think. Yes, that is the correct direction.
Do you want to put any kind of multiplicativity condition on that, on the, say, multiplicative maps from MU to ring spectrum?
I don't think so. There was one source that I was reading this. I don't believe they made a mention of that, but also they could be wrong. And ergo, I could be wrong. Possibly there is a multiplicative assumption there. I don't know. Because also this isn't in Ravenel. Ravenel doesn't discuss complex orientability in any of the sections listed. This is from a different source. But it's nice because given a complex oriented homology theory E, it's going to connect to the formal group laws that Dinglong discussed last week. So if I have some sort of complex orientation XE, there's a canonical map from this, since CP infinity is a H space. This map is just literally the classifying map of tensor 2 complex line bundles, which will end up at another complex line bundle. So it gives a multiplicative structure on CP infinity. If you take the induced map on this gives sort of a coproduct structure. Not exactly, it looks like one. From the complex oriented cohomology at CP infinity to the product, you can use the Atiyah-Herzberg spectral sequence to show some isomorphisms. This ends up just being, if I remember correctly, and this is the same thing, 2 generators. And so if you take a look at what M star does to the element Xe, you'll see can be some power series in these two terms. And because of the associativity and H-space structure in general of CP infinity, this F here is a formal group law. Now this same story, this same story goes for MU. MU has a complex orientation. You can do this. You can get a formal group law out of this. Because of last week's talk, we know that formal group laws are classified by maps from the Lazard ring. So it'll give us a level of theta from the Lazard ring into the homotopy groups of MU, since that's what it's going to be over. It is a theorem of Quillen that this is an isomorphism. Now, the reason that I still want to have that nilpotence theorem up there is this immediately proves Nishida's nilpotence theorem. Basically showing that every element that is not trivial or not degree 0 in the sphere spectrum is nilpotent. Short vote for that. So we have this is the Boardman homomorphism over here. If we apply that to the sphere spectrum theorem, we get a map. By the definition of MU homology, this is the homotopy group MU, which we know to be the Lazard ring from Quillen. Thank you, Quillen. Now, all of the non-degree 0 elements in here are torsion. This ring is torsion free. Therefore, they all have to be in the kernel. Therefore, they're nilpotent. So that is an immediate proof of Nishida's nilpotence theorem, assuming this as one of the theorems we're going to prove during the seminar. So that is the discussion of complex orientation that I wanted to have, just to give some more motivation as to why we want to study this MU. For other spectra, we may not know as much about E to have a nice theory as that. So we might want to study more about the algebraic structure of MU to be able to use this theorem a bit more, and also to end up proving it.
Zach clarified in the chat that he thinks there's a multiplicative assumption going on here.
Sweet. Yeah, I can look at the lecture notes that I read about complex orientation from, and I'll amend my lecture notes that I'll post in the Discord soon.
The assumption comes from this tensor product of, I believe it comes from this tensor product of line bundles.
Okay, so that would end up giving, yeah, the spectrum would be multiplicative to do complex theory anyway.
Yeah, because if you want to get the formal proof law, then you need multiplicativity, so it preserves that product. Yeah, and that's why.
Also, if there was a choice in your XE at the
Yes.
beginning, how does that affect the formal group law?
That should lead to different choices of XE should give, what was it? I believe they're going to give isomorphic formal group laws. I don't know exactly. It shouldn't be too hard to prove that they give isomorphic formal group
Zach
laws.
agrees.
Yeah, they will. For any even periodic homology theory, you can get there's at most one possible formal group law.
Yeah, they're all gonna end up looking the same. Okay. Now we just did a bunch of geometry. We're gonna start doing some algebra now. And Ravenel starts by discussing the story in a more familiar homology theory. So if we just have E as the Eilenberg-MacLane spectrum, which I believe is just denoted K, some pi, but it is the Eilenberg-MacLane spectrum. I really want it to be not P. If we look at the structure that E star of X has on any space X, it's related to the Steenrod operations. So, what do I say? If I let n equals E star E, this is the algebra of Steenrod operations. Any space gets a module structure over this ring. For example, we have a nice little map, and A tensor E star of X, back into E star of X. We can take the algebraic dual of this. We're going to go through a bunch of stuff. Getting a comodule structure, dual Steenrod algebra. And this is a fairly nice structure on this. Not only do we get a co-module structure here, but this is induced by maps on the level of spectra. It's coming from some map that looks like this. Smash X. Comes from something relating to the unit map. Now, the fact that this defines a unique comodule structure on E star of X is a property that is only really special to this Eilenberg-MacLane spectrum. If we go for the story in MU, this doesn't give a unique comodule structure, basically because this thing has a left and a right version. Somewhere. So we have the right version of this. Left version. And thus an action of the form of this would have to be two-sided in some manner. It's going to lead to hot algebroids, as we discussed in the last talk. However, at least for someone like me,
Is there a UIUC somewhere? So when we have that map from E star X to pi star of E smash X, that is E smash E is that A check, right? And then you're only left with an X. Don't you need like an extra E?
This is related. I just put the page down. This is. What do I want to say? I believe it is a property of the multiple. It is a spectral level property that this homotopy group here ends up being. Start tensor over E star. E star X. And then because the Eilenberg-MacLane spectrum is flat, this is an isomorphism onto. This is an isomorphism here. And then we can get into E star X that way. Does that make sense?
So the tensor is over E star.
Yes.
Okay.
And for some reason, just when Ravenel was writing it, he decided to not put the E star there. Thank you, Ravenel. Did you have something to say? So this is what we'd like to have. We can't have this because we have 2 units here. And so we're gonna end up getting hot algebraic structure. Now, yes.
What happens in the Eilenberg-MacLean case this doesn't happen?
These end up representing the same map on homology.
Oh.
And it's just completely and utterly coincidental. We don't have that for the case of MU. So one of the ways that I was trying to reason in my head about why we would want to move to categories from this, because E star over there is kind of defined in hop algebra. Groups are very nice. Why would we want to move to a category? Since hop algebras are co-groups, we can look at what happens if we take homs to certain diagrams. So we have this E star E tensor over E star. E star E mapping into some ring C. This is the pullback over E star E C. This isn't a pullback, it comes from a pullback. We're mapping U star left unit. And this goes over here to that exact same group. See. This map here is induced by the right. Now this sort of statement, we're basically saying this thing acts like a pullback between these two. In my mind, looks like the statement of what you want for the source of morphisms in a group relating to the objects in a group. This thing is basically built out from a source map and a target map, and it needs to be compatible, which is basically what this under tensor is doing. Another motivation is back when from Dinglong's talk, we wanted to sort of capture the idea of formal group laws and the isomorphisms between them. Since there are multiple formal group laws on any given ring, we need an object set, and the isomorphisms between them form the morphism set. So it's 2 different reasons why we might want to give this thing the structure of a cogroupoid. And that is exactly what we get. We get the structure of a hot algebraic. And the diagrams from last talk were very good. I'm just going to put up the maps that are part of this. That's really all we need. Hop algebraic is basically 2 rings over K, where there is a thing that I want to say. Yes, and we basically want it to act like a cogroupoid object. So hom of S and C should be morphisms. Objects, and hom of sigma into C should be the morphisms. This is captured by a coproduct structure. Here is delta. Conjugation, which basically is giving inverse morphisms. With augmentation. So once you hom it, this is going to end up giving identity morphisms. And we have our little friend, the left and right unit. Inducing source and target, as we just saw. And it is a lovely theorem of homotopy theory that if E is flat, homotopy commutative, ring spectrum, then the pair I star E and E star E have the structure of a hop algebraic with all of the maps that we've mentioned. It's not too hard to get the other ones after this. And if the spectrum is P local, if it's just normal, you get a hot algebraic over Z, it's P local. UIUC, which is, I believe the integers localize that P and not the p-adics. I'm pretty sure if you would put the p-adics, there'd be a little hat there. That's what we have there. That gives us some structure.
So you mentioned in the Eilenberg-McLean case, something
Mhm.
trivial happened.
Yes.
So in terms of the Hopf algebroid structure, is there something you can say about like what degenerates over there?
In that case, these would end up looking the same. And so we would basically remove any of the source and targetedness. It would end up looking like one object, and boom, we have a Hopf algebra, not a Hopf algebroid.
Okay, great.
This section of the talk is basically going to be devoted to showing that Hopf algebroid truly does represent formal group laws and the isomorphisms between them. Because that is a very important part of this seminar going forward. For that, I'm going to define left comodules over Hopf algebroid. It is the left S module M together with a S left S here. Structure map called psi from M into this tensor product. It looks almost similar like a normal local module, except we have this tensor over S. And that has to be co-unitable and co-associated, which is a bunch of diagrams that I'm not going to draw out. It is what you would expect it to be, basically. Right comodules can be defined similarly. You take everything that I said on the left and you put it on the right. And then there's also comodule algebras, where this thing has algebra now. And this thing is required to be a homomorphism of algebras. One of the reasons for talking about left and right comodules is we want to show that the MU homology groups of a space X have a right comodule structure over that Hopf algebroid. So again, linking back to the periodicity theorem, that's going to give us some structure with which we can attack this thing to show, hey, what kind of elements can be nilpotent.
And then assuming if we want this to be an algebra or a co-algebra, I guess. We're taking sigma there with the S bi-algebra structure from the units.
Yes, exactly.
Okay.
Exactly. Yes. I think I already wrote this on the board. I don't know. We get a proposition that basically links to that. E is again a flat commutative ring spectrum, which is what we're going to see basically during this talk now. This thing naturally gets a left commodule structure. Which is induced by this structure map on the level of spectra. So this ends up giving the structure of the homology groups as a left E module structure, again with the tensor that we discussed last board or so. So now this is sort of the proof heavy section of the talk. It's basically going to be devoted to studying that Hopf algebroid structure. There are going to be two theorems I'm just going to throw at you. The first of which I at least have an ability to point to a source, and the second, there's a name of it. So this is theorem due to Milnor and Nilpotence. And the restatement of what Quillen's theorem is, just with some nice notation that we're going to use later on. The homotopy groups of the MU spectrum is freely generated on these generators we call epsilon up to infinity. The degree of xi is 2i. And these generators can be chosen very, very nicely, so that if I take the Ravenel homomorphism I have the other board at the start, the Ravenel homomorphism on these things, going into the homology groups are these elements bi plus decomposable. Here about. This is in the case that I is p, k, minus 1. Otherwise, these BIs are generators of the homology ring. They have the same degree. They're going to show up a little bit later. Now that gives the homotopy groups. We can see. I want it here. This is the Hopf algebroid that we want to consider. Right now, we have described pi star mu. Now I'm going to give it a description of mu star mu. This is due to line waiver. And now the top. This theorem states mu star of mu is just a freely generated ring over the homotopy ring of mu on these generators bi from over there. The left unit, which wants to take mu star into this, is just the inclusion. Literally just taking the elements here, putting them in degree 0. The right unit and other things are more complicated, much more complicated in fact. It is described by this, in my opinion, god awful description. Don't worry, I will explain what MI is in a half second. Okay. That is the description of the right unit. It looks very ugly. Conjugation on these MI dudes, nicer. Of course, it goes back to the right unit. Disgusting. And then conjugation generally on the BI elements. BI. And one thing I want to say, this thing should sort of remind you of taking the inverse of an isomorphism on the fundamental groups. This, as we're going to see, is related to a sort of inverse recomposition kind of thing.
Is that epsilon BJ there?
These are all C's. CBJ over there, CBJ.
And in the other part of that sum, to the isosome part.
That is a thank you. I should have put that. These are all sums. So yeah, you can see utterly terrible, double sum, all infinite. The way you can get at, I mean, obviously this doesn't look like it's explaining one of the right units. You basically have to like sum out the terms and look at them in the right degree. It's generally a terrible procedure. But what we get, so I don't have too much time, so I'm gonna do this here quickly. If gamma R is the group that Dinglong was talking about the last lecture, which basically classifies isomorphisms, they look like power series of the form x plus b1 x squared. This thing is isomorphic to of this hop algebroid B. The important part about A, the coproduct. So this is the description of the coproduct on mu star mu. You can see that it doesn't land with coefficients in the homotopy group of mu, but with integer coefficients. That basically means we have a hop algebra sitting inside of this hop algebroid. And the structure of the hop algebroid itself is sort of governed by the structure of that hop algebra plus the right unit. That is where this B is. This B is the hop algebra Z generated on those BIs. There was a theorem basically saying that the group of isomorphisms of fundamental group laws over a ring R, which is this thing, is isomorphic to the hom of that hop algebra into R. I believe it's a proof that was given in the last talk. This gives our hop algebroid a structure of a split hop algebroid, which again basically means it's generated over that hop algebra plus a ring plus a right unit. I discussed it a little in the lecture notes. I'm going to skip that over as of now. But 2 minutes. From last talk, we know that we have logarithms of formal groups. Two properties that are discussed. Use pretty soon. Is the fact that logarithms act multiplicatively over a formal group. And the logarithm, the universal formal group over pi star mu is related to these mi elements, which basically come from the interpretation of the homotopy ring as a complex cobordism ring. The other fact that we are going to need, and this is the last thing that I'm going to give before going to the proof. If I look at the logarithm of formal group law acted on by an isomorphism, this is exactly the same as this. It's a nice proof. Ravenel doesn't complete it fully. It's kind of weird, but I'm pretty sure you can do it by looking at Taylor series expansions. I believe that's what he's talking about. But now this is the actual part of the theorem that's important. So if we have a map from mu star mu into a ring R, we can get some nice compositions. Firstly, from the theorem over there, saying that hom B into R is the same as an isomorphism. This thing gives an isomorphism of formal groups. Can't talk. If we look at the compositions as this goes over here, this is a map of mu star into R. This gives two different formal groups. Comparing logarithms, let's call this thing the formal group law F. Let's call that the formal group law. Delete the right unit. We compare formal group laws. This thing ends up being we have these two statements. If we'd like to show that this is true, basically saying that this truly does classify a isomorphism, it's equivalent to showing that log f is log of this acting on it, and that is not difficult at all. Basically, if you act on this, the formula for this action is exactly the same as the formula for the right action on this with the right unit. I have a proof in the notes. It's actually pretty decent. Kind of happy with it. Unfortunately, time. I can immediately prove that this log of f prime is just this. Basically saying that this sort of coalgebra structure truly does capture formal group laws and isomorphisms between them. I have one more section in the lecture notes that basically go into some algebraic structure relating from this. It's not too important. We're going to see the effects of it in later talks. But yeah, that is MU theory and how it can lead to some really nice algebraic properties that we're going to use in the seminar. Resulting questions about written?
Good question, what is flat?
Oh God. So the way that Ravenel described it is, actually the way that I heard it described is flatness is the property that guarantees us star I star E. It's isomorphic to something. Where is it? Where is it? Where is it? Somewhere in here, I know. Yeah, probably. As a property, if I remember correctly, it's saying that some modules over pi star E are flat. I'm pretty sure it's saying something along this line. But this sort of module is a flat module. We'll replace that with an X.
So the confusing thing about this, I had a discussion about this on the Outbreak Ecology Discord server last week, and there's like an MO discussion about it as well. So it doesn't actually have anything to do with flatness in the sense that we would usually use it, or why Ravenel called it that. Nobody really knows.
Yeah.
I guess you could ask him, but it's more akin to being free. And in fact, it can be explicitly described as the condition that that E is free over something like that.
Yeah, I think there was I looked it up. There was like an NLab glossary that had a definition of it. I don't know if it's the right definition, but it's a definition.
There's 3 different definitions of flat, and they're all different.
Great.
Wait, is this flatness the same thing that shows up in the land of great flatness, or is
I
it a
don't-
different thing?
Unrelated.
Okay.
Yeah.
I was wondering like a historical thing, the Milner-Novikov theorem you wrote
Yes.
down. Did that come before Quillen's theorem?
In the way that I understand it, it did. So Quillen's
Quillen like
theorem-
could have used that representation of MU star.
Yes, I think the way that it goes, a proof of Quillen's theorem is in Blurry's notes. But the first part is basically showing that if you tensor this and you make it a rational statement, that this isomorphism is true. And I believe that this uses Milner-Novikov to show that that is true. And then once you do it rationally, the second part is to use the atom spectral sequence to show that it's true p-adically. So show. And that will end up showing that it is true integrally. I remember correctly, that's the way it goes. And it is in Blurry's Chromatic homotopy notes. I'd like to say around lecture 10. That's my best guess.
Well, so I double checked, and the flatness condition that Ravenel uses is equivalent to the condition that E star E is free over pi star e,
Oh,
or sorry,
that was
over
close.
pi 0 e. And that is not related to flatness of the infinity rings in Lurie's sense. Although it does imply a certain flatness condition, but it's also related to that.
Sure, yeah, the way that I've heard it described, it's the condition that makes that work.
Yeah.
And I think you just smile and nod and accept it as a fact.
I'll try to share this MO discussion in the Discord that I found it pretty much.
Any other questions?
Alright, so thank Garrett again.